आपने पूछा था ना, ये सिंपल आंसर है, ठीक है। बाद में भी मुझसे पूछ लेना। जी लाइट्स कम है। बेटर नाउ। All right, so today we are going to learn the physics of system of particles. Okay, so and in this chapter, which is titled as system of particles, we would be learning some new physics concepts, okay, and new laws as well, some very fundamental laws. But also I promise that you would be learning literally the rocket science, okay. It would be something about rockets. You would also be learning why it is more tricky to get on a boat, to step on a boat, than to get into a car, for example. You would also be learning, or we would also be learning, that what you should watch out when you go buy a gold chain at goldsmiths, okay. There is a trick, and physics helps you understand that, okay. So, but more importantly, until now we have been treating objects of finite sizes, objects such as myself, a human body, objects such as car and a plane, okay, or earth itself. We have been treating them as point particles, but that's unrealistic, isn't it? These objects are not really point particles, they have finite sizes. And the fundamental laws that we learned, 3 laws of Newton and the law of conservation of energy, these 3, basically 4 laws, help us solve the dynamics. We have only been applying those laws, or the way we have learned them, in the context of just a point particle, okay. Now we are going to learn how to apply it to a realistic system, okay, a system with finite size. All right, but we would still be basically dealing with point particles. What I'm really going to do is to justify more rigorously why treating an object of finite size, for example a car or a planet or a human body, as a point object is a reasonable assumption, okay, in the context of Newton's laws of motion, okay, using basically Newton's laws of motion, combining them together. And we would be learning how to deal with a system of particles, and how we can again, in a special case, reduce the dynamics of a system of particles, an object of finite size, to again a point particle, okay. And what does it mean? When you have a realistic object, for example this chalk, when I throw it up, okay, is it really just tracing a parabola? Let's say the friction is not there, so what is its trajectory? No.
So it depends on now it is.
It is a parabola, right? But look carefully. Look carefully. Is it really tracing a parabola? Look, let me draw it here. The way I throw it, right? Because if you look closely, it's also rotating. Now I can certainly trace a line through it that makes a parabola. Only one point in this object traces actually a parabola, and the other points really have a much more complicated motion. The trajectories are not a parabola. Okay? Now this is the difference between when you have a point particle and when you have a particle or an object which has finite size. Now this additional motion, which is more complicated to describe, is because there are two types of motion involved in here. One, we technically call it translational motion, the motion from here to there, okay? And the other motion is the rotational motion. More formally, we deal with rotational motion in the next section, in the next chapter, okay? Later in this course. But you must understand that once you have an object with finite size, that its motion is more complicated, and every particle, every point on this object is not moving in the same fashion. Only one point in this object, a privileged one, a special point, ठीक है ना, traces that trajectory. Okay? Okay, so now I just said that a realistic particle is not just one point, but it's a collection of lots of points. Can you tell me the number of points in this object?
Not infinite. Number of atoms, I said.
Number of atoms. So let's say that I have a concocted number here. Let's say that I have a piece of metal, a piece of iron, which weighs, whose mass is approximately 55.6 grams, a piece of iron. What are the number of atoms in it? Avogadro's number, Na. Okay, so for our purpose, this is nearly infinite. You know, what is the value? 6.022 10 to the power 23 atoms. Now imagine that if I had to write Newton's law for each one of the atoms in this system and then solve it, we are really doomed, right? We cannot really solve a system atom by atom. There must be a way out, okay? And there are two ways out, one for rigid objects and one for non-rigid objects. We would be today dealing with rigid objects. Thankfully, there is a way out. And for non-rigid objects, there is a whole new branch of physics, okay? But you would bits of it you would learn in modern physics, the thermodynamics, okay? And statistical mechanics is called, okay? But for rigid objects, it's relatively simpler. So we would deal with that today. So you understand the kind of problem we are trying to simplify? Or the amplitude or the complexity of it? So now instead of writing the Avogadro's number, well, basically we can. In principle, nobody stops us from doing this, that I write an equation of motion for particle 1 in this sample, and then m1 a1, right? One equation, second equation. I'm just writing the Newton's second law, right? And this would, of course, describe the motion of one atom. This would describe the second atom, m1, sorry, m2, a2, and so on. And finally, F and A, the 6.022 10 to the power 20th atom, right? And its mass, Na, and its acceleration, right? Now, if I could just combine these equations together, then I would have a way to describe the dynamics of a piece of metal whose weight is 55 grams. And that is precisely what we are going to try to do today. Okay? We're starting with one particle, and then we're trying to combine the motion of all particles to arrive at something simpler, to arrive at something that we can deal with. Okay? To arrive at something that is practical. Okay, do you have an explanation for this behavior, for example? Do you understand why when we throw an object, one particle on this, one point on this object here, follows the trajectory, the parabola, which gravity predicts, which if we use the Newton's second law, wait, let me complete the question, okay? But the other points, all other points except for that privileged point, that special point, all other points at the ends, in the middle, here, wait, here, they are not tracing a parabola. Why is that? Yes, now?
Sir, because it's in the center and other points have angular momentum. Center वाले का कोई angular momentum नहीं होगा.
Yes, but we haven't really introduced the angular momentum yet, so I want a simpler answer. That doesn't involve angular momentum. Let me see. Yes. That's true, but that doesn't explain why other particles behave differently. Yes?
All the particles are experiencing a torque around the center of gravity.
Yes and no, because there is no external force other than gravity. So that's not the answer. Yes?
They are moving about that point.
And that's true, but this still doesn't explain why they are moving differently. Who else? Who else? Yes, you? No, but even if they had same masses, because let's say it's a piece of iron, so if every atom has the same mass, that's not the answer. But thank you for entertaining me.
Oh, sorry, I figured my answer was wrong.
You withdraw.
No, but only you that if you throw it with an initial torque, otherwise it can follow the normal.
Yes and no, yes and no. Yes?
Sir, the component of weight is providing expression for all the other points. इसके अंदर only the जो उसके perpendicular है G, that's providing the expression. जो the center.
No. The answer is, whenever you have a system of particles, there is something new that comes in. Let's say that you have a system of particles. Let's say that this is your object. Okay? A very irregular object. Okay? Or let me just take a more simpler example. Okay? So what happens is that each point, now this is your system. Let me draw a boundary around it. This is your system of particles, okay? Now you have two categories of forces, two types of forces. Of course, this is a rigid system. It means the particles are tied to each other. There are forces within the system, aren't there? Right? If that was not the case, then this chalk would just break away. So there are internal forces that they exert on each other. Okay? And then there are external forces, okay, that come from the outside of the system. So when I'm throwing this chalk above, the electrostatic attraction between two atoms inside this chalk, is it an internal force or an external force? Internal force. What about gravity? Gravity is external force. The reason why different particles on this object behave differently is because these particles are not experiencing the same internal forces. They are experiencing different internal forces. All right? However, that privileged point, that special point, does not see any internal force. It only responds to, it only sees external force. And now we have solved this problem for a point particle. Of course, in case of a point system, there are no internal forces because just one object. And a point object, when we throw in gravity, traces what? A parabola. So in a system, in an object of finite size, the one point which traces parabola, we can already tell before solving any equations that it does not experience any internal forces. Now we would see that more quantitatively in a minute. Yes?
Why are internal forces different?
We'll see that. Now, to make the argument more quantitative but also tractable so that we are able to understand it, instead of taking n particles or Avogadro's number of particles, I'm going to just take 2 particles. Okay? This is still good enough because we have not 1 particle, we have 2 particles, right? And once we understand the equations for 2 particles, very easily we can generalize those equations to n particles or any number of particles for that matter, right? So we have mass 1 m, and we have another mass attached to this mass m2 through a rigid rod. This is very important. Through a rigid rod of mass mr. All right. Now you throw this object in the air, and it's going to execute similar motion as this chalk, right? It's going to rotate, and also it's going to track at least one point on this object is going to trace a parabola. Okay. Now we look at each of these particles as a point particle and apply Newton's second law and try writing the free body diagrams. Okay. And this is happening in the presence of gravity. All right. And I'm drawing a circle around it to say that this is the system, and any force that comes into the system from outside is an external force, and all the forces between this particle and the rod, forces between this particle and the rod are internal forces. Okay? The system is complex enough to make the point about system of particles, but is simple enough to understand because we have just 2 particles attached to each other through a rigid rod. All right, so we take m1 first. Okay, what are the forces acting on it? So let's not write it mg. There is one external force. I'm just writing this as F1e, and by this notation I mean the external force acting on mass 1. Okay. Now there is a force that this rod is exerting on this mass 1. That is my second force, and now that force is going to be, and let me just write the notation. So that is 1r. Okay, that is the force that rod is exerting on this mass. Okay, 1r, this is what 1r means, and 1e means external force on object 1. Is there any other force acting on this object m1? No other force. Gravity, this external force is gravity. Okay, I'm just writing it in general terms, but yes, this is external force, right? One external force acting on m1 and one internal force acting on m1, just 2 forces. Now I can write the Newton's second law for this point particle, which becomes, remember the original definition of Newton's second law, sum of all forces is equal to mass times acceleration. Okay. So sum of all forces means F1e plus F1r is equal to m1 times a1. All right. And for a later use, can I also write it like this? m1 d squared r1 over dt squared, right? That's just acceleration. Twice the time derivative of position vector is acceleration. Now similarly, what are the forces acting on m2? One external force 2E and one internal force 2R, right? Just two forces acting on m2. So now for m2 I can again write 2E plus F2R is equal to m2 d squared r2 over dt squared, right? And now I need a third equation. Let's call this 1. Let's call this 2. And now the third equation is for the rod. Okay, again we are treating the rod as a point particle. Okay, so one external force, that is simple, Re, and how many internal forces? Two internal forces. Okay, one exerted by m1 on the rod and the other m2 on the rod. Okay, so that then using the same notation becomes R1 plus FR2 is equal to MR d squared R over dt squared. All good? Right? So now let's add all these equations together. Okay, so if you add all those equations together, you will get a single equation for the whole system. All right, and if you add them all together, then this becomes F1E plus F1R plus F2E plus F2R plus FRE plus FR1 plus FR2 is equal to m1 d squared r1 over dt squared plus m2 d squared r2 over dt squared plus mr d squared rr over dt squared. Okay, so does this equation make sense? I've just added all those three equations together. Now see this, that this F1R is the force that rod exerts on the mass. There is an equal and opposite force that the mass exerts on the rod. So can I write this relationship here? Let me use a different color. That basically F1R is equal to minus FR1. That's all right. Now this was Newton's second law and this is Newton's third law. This also means that F1R plus FR1 vectors equals to 0. ठीक है, तो इसका मतलब ये है कि F1R added to, sorry, no, this is not, F1R added to FR1 is 0, so they cancel. F2R is R2. This sum is also 0. All right, the equation simplifies, right? So let me rewrite the equation now here. And the equation becomes F1E plus F2E plus FRE is equal to M1 d squared R1 over dt squared plus M2 d squared R2 over dt squared plus M3 d square, thank you, drr over dt squared. And lo and behold, on the left side we have no internal force left, only external force. Okay, and I can just write it as the net external force, right? The total external force. So this becomes just simply Fe, where Fe is equal to F1E, F2E, FRE. On the right hand side, I still have the same thing. Now this has started looking like Newton's second law, isn't it? Yes, please. Yes, yes. तीन फोर्सेस हैं, ये बात कर रहे हैं. यस, नहीं, this is the acceleration of the rod just. Because look, in these equations, let me say this again. I've said this before. The acceleration of an object is determined by the forces acting on that object. Okay, so for M1's case, these are only two forces acting on it, one internal, one external. In M2's case, two forces, one external, one internal. In rod's case, there are two internal forces. Okay, you can also think of, I said this, that forces are interactions. How many objects this rod is touching? Two. There are going to be two interactions, two internal forces, and then one external force. Okay, so there are these two internal forces are acting on the rod, and internal forces, and so is the one external force. So all three forces are acting on the rod, and the acceleration on the right hand side is of the rod, not the whole object.
So right hand side law में आपने F1R equals to FR1.
That is true, because the force that mass exerts on the rod is equal and opposite to the force that rod exerts on the mass. That is why this is true. It is independent of rotation or anything else. Yes?
Sir, even though M1 and M2 are not in contact with each other, why is it there a gravitational force? That is also independent.
There is no, there is what?
Sir, M1 और M2 एक दूसरे को touch नहीं कर रहे.
Yes?
But उनके दरमियान में एक gravitational force of attraction है.
वो हम इग्नोर कर रहे हैं. ठीक है, नहीं सॉरी, अगर उसको नाम भी इग्नोर करें ना, ठीक है, वो डायरेक्ट जो उनके दरमियान ग्रेविटेशनल फोर्स है ना, दैट वी आर इग्नोरिंग. So there is no, yes, that's a good point, but it's a fine one. Okay,
That would also
so
accelerate.
but they would also make an action reaction pair. Okay, and that would again be an internal force. Okay, good. Negligible, but even if you consider it, it would make an action reaction pair. All right, so now you see this has started looking like Newton's second law, right, applied to a system of particles. But on the right hand side, I don't get something nice, a single acceleration, right? If I could tidy the right side up, I would probably have something simpler to deal with, describing the motion or dynamics of a system of particles. All right, now we are going to do some algebraic and calculus tweaking of the right hand side. The first one I want to do is, just let me write it again for you so that it's consistent. So we are defining a new quantity here, okay, that is capital M, which is M1 plus M2 plus Mr, okay, the total mass of the system. All the masses summed together give you the total mass of the system. And of course the analysis we are doing, it has two assumptions, okay. One assumption is that the mass of the system remains constant, the total mass of the system. If the total mass of the system doesn't remain constant, then this analysis is not valid, and also that this is a rigid object, okay. So we have a new quantity. Then I want to also see this. Let's say that I have Mr, okay, or rather M over M. Both masses are constant. This mass is constant and this mass is constant. Now if I take a double time derivative of this quantity, what am I going to get? No, I mean analytically. M over M d squared. Is this right? Of course, because it's constant. Fine? No problem with this, right? Okay, now let's multiply this equation. On the right side, both multiply and divide with M, this equation. So multiply and divide with capital M, okay, on the same side. Doesn't make any difference, does it? Where M is equal to? All right. So then can I write now Fe, the total external force acting on the system of particles, equals one over M. Now is it 1 over M or is the other way? No. Sorry. M d squared over dt squared. Watch carefully, okay. M1 over M R1. This is all right, right? So once you take the derivative, M1 over M would come outside. And this M is multiplied to the whole thing. D squared over dt squared M2 over M R2. Okay. Similarly, Mr over M R and the whole thing. This is all right, right? Just some algebraic tweaking. Okay. Now one more thing. If you have this situation, Mr1 over M plus M1 over M R1 plus M1 over M M2 over MM R2, and the double derivative of the whole thing, isn't this equal to plus do you see this? Right? You can write this, right? So basically I can write this derivative outside. And this becomes M, capital M, and M1 R1 R2 plus MR R. How about this? Okay, so now we have gotten something a bit more nicer than before. Okay, this looks more like Newton's second law, right? Because we have at least one derivative now here. Okay. Now, if you carefully look at the general statement of the Newton's second law, let me write it in color for you. Look at this and compare it with this equation. What do you think is this quantity? What would this quantity be? Position of something, right? We don't know yet what, but position vector, right? Look at that. It indeed is a position vector. That remains to be decided. Position vector of what? That is the position vector of the center of mass of the object. And that is its rigorous mathematical definition. R, capital R, so we write it as capital R. So let me just use it on the next board. So now R is, and I'll do more to convince you, okay, that it makes sense. M1 R1 plus M2 R2 plus MR RR, okay, divided by total mass, okay. I've just defined something and now I substitute it back and rewrite the Newton's second law or the equation of motion for a system of particles, right, that we are dealing with. A system of three particles, two particles attached through a rigid rod to each other. So Fe m d squared over dt squared r low. Now this, see, looks much more simpler, doesn't it? This is now standard Newton's law being applied to a system of particles. Okay. Now what is R? What is R? R, I have already said that it is the center of mass. It is the coordinate, it is the position vector of that special point in a system of particles which simply follows or responds to only the external forces, and then follows, in case of gravity, the standard parabolic path, how other particles do not. Okay. Another way of looking at is, if you look at carefully, this is the mass weighted, carefully, the mass weighted average position of all the particles. You are taking the position vector for each particle, multiplying it with mass, so that if it has larger mass, it gets larger share, larger say in determining where this R would be. Then taking the position vector of the second particle, multiplying it with that particle's mass, so that it gets its fair share of say or opinion in, okay, or physical impact or physical influence, if you like, to determine where that R would be. And then the same for this, and then you're dividing the whole thing with the total mass, so that is mass weighted average position. And that is, just a minute, that is the center of mass. Another way of looking at it. Yes, please. देखिए नहीं देखिए मेरी बात सुने. This is mass weighted average position because इसकी dimensions क्या होंगी? नहीं, इस पूरे ऑब्जेक्ट की जो डायमेंशंस हैं mass की हैं या पोजीशन की हैं? जी नहीं, then we are also dividing it with mass, so it's नहीं, its average position is mass weighted average position. Yes, but I'm multiplying them with masses as well and then dividing by the total mass. Is mass weighted average position. I can show you by an example in a minute, okay, if you give me a few seconds, okay.
So इसमें mass cancel नहीं हो जाएगा?
कौन सा mass?
Full equation में capital M.
कैसे कैंसिल होगा? देखो ये तो मैंने इंट्रोड्यूस करवाया ना, टू इंट्रोड्यूस दिस कॉन्सेप्ट, ठीक है, दिस इज आर, ठीक है, एंड देन अभी वी हैव टू इंटरप्रेट दिस, ओके, वी हैव टू इंटरप्रेट दिस इक्वेशन, ओके, but let me just show you first a quick example how this is average weighted position, okay. Let's use this board here. Okay, so let's say that in a coordinate system, okay, x and y, you have an object sitting, quiet please, 2 units along y-axis and 1 unit along x-axis, and its mass is 3 kilograms. All right. What is its position vector? R1. Can you write R1? 1ex plus 2 ey. Okay. This is your mass 1. All right, should be all right, and then you have a second mass sitting at 3 units along x-axis and 2 units along y-axis, m2, and it also has 3 kilograms. Okay, and its position vector is R2 is 3ex plus 2ey. Okay, now we have these two particles of identical masses. Now let's calculate the center of mass. Okay, so how do we calculate the center of mass? Exactly using that definition, the position of the center of mass. Okay, R would be M1 R1 plus M2 R2 divided by total mass. Okay, so what is M1 R1? 3ex plus 6ey. Can I directly write it here? 3ex plus 6ey. What is M2 R2? 9ex plus
6 even. Yes, sir. Hold your hand.
Okay, so 9ex plus 6ey, and then divided with what? 6. Okay, so now this 3x and 9ex becomes 1, 12ex, 6ey plus 6ey, divided by 6. If we simplify this, what does it become? 2ex plus 2ey. So which is where? Exactly in the middle. Exactly in the middle. Once you have the masses same, then weighting the position with masses doesn't mean anything because everybody contributes the same. You can take the mass outside, and that would be exactly this, cancels it, and then you can just take R1 plus R2 and divide it by the number of particles that you have, the number of position vectors by the same number, and that is your average position. which is this case. If you just taken those vectors together, added them together and divided by 2 because the masses are same. But once the masses are not same, then you need to have weighted average, then you can't take the masses common. Okay. Now let's repeat this example, making the masses different. Let's make mass 2 equals to 4 kilogram. Okay, and then the rest of this analysis remains the same. The only thing that changes is this vector here. Okay, this becomes 12. And this becomes 8. Okay, and the sum becomes 7. For okay, so now you sum this everything together, and 3x plus 12x becomes 15x plus 6 and 18 14 divided by 7. This becomes 2.5 ex plus 2 ey. Okay, so this means, what does it mean? It means that when this mass is heavier, it had more contribution in determining the vector, and the center of mass has slightly shifted to by a half a point towards right.
15 over 7 is not
Oh, sorry, what is this? Sorry, 2 point what? 2.14? This?
Yes, sir.
All right, but still the point remains, right? It has shifted towards right. That is what it means, the weighted average. Okay, and it is still the average position. Okay, because you are summing all the positions, multiplying with masses, and if all the masses are the same, then what you will get here, this is just the number of particles, n. Now, interpretation of this equation, I'll show you with an example as well, but first look at this. What this means is that once you apply the Newton's second law and third law together, and of course this analysis is only valid in inertial frames because second law is only valid in inertial frames, there is one special point which only sees the external forces. And so you could treat that special point as if all the mass belongs to it. The center of mass behaves a point particle of total mass m. Okay, it replaces all the masses and all the distances with total mass and takes on this position and responds to external force as if all the external forces, it was only seeing the external forces. So this means as if all the mass is concentrated at one point and that point particle only sees external forces, no internal forces, and then you can just simply apply the Newton's second law to that, and at least you can calculate the dynamics of one point in an object which has a very simple force relationship. All right? Yes? Of course, the other points are not going to follow this simple relationship. This is only the center of mass. But this gives you a good enough idea, if the particle is small enough, that how the overall object is going to move. Okay. They would not, because the internal forces are different on them.
तो अगर उसकी mass density different हो तो उसकी फर्क पड़ेगा उसकी trajectory का.
Of course, उसके बारे में बात करें, but his question is that if you have an object whose mass density is different, look, if I was to generalize this and there was n particles, then I would be writing this as, for n particles, this R would generalize as, this would become a sum from 1 to n m1 r1, right, divided by sum 1 to n mi, this would be I, this would be I. So this would be that total mass, this would be total mass, and this would be, but you see this is sum. So what is this? This is integration. If you take that the matter is composed of not discrete particles but a continuous mass, then these both becomes integrals. Okay, then here you can write density and integrate over all space, and that would give you the mass, and take into account if the object has non-uniform density. All right, we will do this again. Okay, so but what I want to say is there is a significant part of this chapter, and the next lecture we would be spending on how to find the center of mass, because once we can find the center of mass for a finite object, at least we can describe its motion, the center of mass's motion, using Newton's second law, using relatively simple equation. All right, so this now the only trick or the only difficulty left when we have an object like a triangle or a square or a sphere is how to find its center of mass. If we can find its center of mass, then we can describe the center of mass's motion using just this simple equation. All we have to do with is to identify the external forces as before, and we can treat it as a point particle. The only difference is now its mass is not just the mass of the particle actually sitting there. It's the sum of all masses, and its position is not, there is no guess game. Its position is the mass weighted average position of all objects. Yes, questions? Yes?
Does it only apply for small objects?
No, it applies to all kinds of objects.
But like the bigger you get, those sweet density would not take into account. Because the actual object है.
Yes, if the object has non-uniform density, look, there is, you see what happened when we had more mass on this side? The center of mass shifts. Now if you imagine an object of non-uniform, so wherever is the average position, the center of mass is going to go there. So like if you have a circular sheet of metal of uniform density, where is the center of mass? In the center. But if it has non-uniform density, then the center of mass would be away from the center. So that's it.
So what about the composite objects? Just with different density?
Of course, calculating their center of mass would be very difficult, but nevertheless, there is a defined quantity and you can always calculate it.
Would that be the same way?
Would that be?
The same method?
Yes, of course, but you would have to do the integration if you know the density, otherwise you can't do that. Yes?
Sir, I had a question. Sir, हम चाह रहे थे कि we didn't want to take the object as a point mass, right?
Yes.
हमने each point का position vector अलग निकालना चाहा. तो सर जब आपने ऊपर force निकाली है, force of 1 on E जो पूरा दिया है, तो सर आपने position vector mass 1 का सिर्फ एक point का क्यों किया? Why not the all points का position vector different नहीं होगा? तो वो हर point external internal force जो लगाएगा different points पे, तो वो as आपने R1
देखिए मैंने जो सिस्टम ऑफ पार्टिकल कंसिडर किया है ना, वो 3 पार्टिकल्स हैं तो 3 पोजीशन वेक्टर्स हैं. नहीं देखो, I wanted to make a tractable position. These masses themselves are point. The whole object is not point, has a finite size, but all these 3 objects involved are point, and I am treating them as point particles. That's why only 3 position vectors. Okay, good. Yes.
So in case of a mass, if the line of action of force is through the center of mass, तब तो बाकी सारा object भी वही trajectory follow करता है जो center of mass follow करता है.
Yes, but initial conditions can change. Yes, there are 2 reasons. If the force is not through the center of mass, that we would deal with in next chapter. Okay, rotations, and if there is an initial initial energy, initial kick which spins it, of course then the motion is going to be different. Okay? Now this looks very simple enough, but this is very important. Okay? This has profound implications. Okay? If all the internal forces on this object in the center of mass frame of reference, in the center, if you were standing at the center of mass of this object, okay, and then looking at all the forces on all particles, if those forces were not zero, what would happen?
Object burst.
The object would burst. Very good. Because different particles have non-zero forces, they would be some would be coming in, and the other, it could collapse as well, or it could just start deforming. A rigid object maintains its shape because all the forces pairwise cancel each other in the center of mass frame of reference. Otherwise, this chalk would either be exploding or imploding or just deforming. That is why how molecules remain stable, and when you shine light and you excite an electron, you create local charge imbalance. Okay? And that creates non-zero internal forces and the molecule splits. Okay? So you interfere with the internal forces of a molecule and you can break it. And as long as the internal forces are balanced, the molecule stays stable. And this physics, this simple physics, is still used to describe protein dynamics, proteomics. This is still used to describe the motion of molecules. Okay? Yes?
इंटीग्रेशन पे क्या होगा
यार बाद में अभी इस तक यहाँ तक समझो ना, बाद में समझा लो, आपको खुद फिगर आउट कर लेना चाहिए. Okay, more.
Just to clarify, it's just to show that if you have a system of particles, you can translate that into one single particle.
Yes, excellent. Thank you very much for saying that. Yes, that's what I was trying to say. That the original assumption when we were treating objects of finite size, non-zero size, the objects which were collection of infinite number of particles, we were reducing them or treating them as point particles, and that assumption was not baseless. Okay? Now let's see that you have this dumbbell actually, and you're throwing it in the air. Okay? So what are the external forces on this? 3 external forces on 3 objects, 3 parts. So here you have m1g Ey with a minus sign, and here you have minus mrg Ey, and here you have on this object minus m2 g Ey. These are all the external forces acting. Now let's do that. Now let's plug these 3 forces here. Okay, on the left hand side. So you get what? Minus m1 plus m2 plus mr g Ey. All right, and on the right hand side you have m d square over r over dt squared. Okay, so this is what capital M, it cancels with this one, and what is left is this, of course, Ey. Okay, and what is left is this. The acceleration of the center of mass is equal to what? Minus g. You see, the center of mass, no role of the internal forces. The center of mass is going to fall exactly like a point particle in the gravitational field of total mass m, right? Now I want to generalize this in the next 10 minutes, because we had just 3 particles, right? But in reality you can have Avogadro's number of particles or even more. Okay? So does this analysis stand if we extend it to a large number of particles? So let's say that you have a system that looks like this, okay? And there are n number of particles in it. Each particle has its own mass m1 and m1, m2, m3, and each particle has its own position vector. Okay? Now all these particles are interacting. Okay? Each particle is interacting with another particle in the system, and they are also experiencing external forces. So if I were to write the force, all the forces acting on particle 1, what would I write? All the external forces together acting on particle 1. These are all the forces acting on, both internal and external. Okay? F1 is all the particles, all the forces internal and external acting on particle 1. So I begin with just clumping all the external forces together as Fe1, all the external forces acting on particle 1, and then I move on to internal forces. Okay? The force acting on 1 due to particle 2, okay, F12, the force, I have chosen a given particle. So this is particle 1, okay. It is experiencing some external force, F1e, and all other internal forces. Okay, so I'm writing the sum of all the forces that are acting on this particle 1. So I have just lumped all the external forces together as one force, and now I'm writing internal forces one by one. Okay, now this is the force on particle 1 due to particle 2. This is the force on particle 1 due to particle 3, and this is the force on particle 1 due to particle n, and this of course is going to be equal to m1 d squared r1 over dt squared. Okay? Similarly, now I can write all the forces acting on particle 2. So I'm lumping all the external forces acting on particle 2 as 2e, and then I have F21, the force that particle 1 is exerting on 2. Then I have F23, and then I have F2n, and this of course is equal to d squared r2 over dt squared. Now notice one thing. In both of these equations, in this case F11 is missing, and in this case F22 is missing. What is F11? A self-interaction, the force that particle exerts on itself. A particle cannot exert any force on itself. That is why there is no F11. There is going to be no F22. There is going to be no F33. Well, atom भी ले लें, कुछ और भी particles होता है. It can be molecule. It's something that you can represent. But you can, वही तो है ना, जैसे हमने दूसरी masses को point particle है. Whatever particle we are considering, we are assuming, yes, this is a good question, because the physicist, and particularly, I shouldn't say on camera, physicists who do a particular specialization in physics have this idea of this obsession with reductionism, that we want to find the most fundamental particle. So say we have atom, but then atom has internal structure, electrons and protons, and then you have protons, or inside protons you have quarks, but maybe quarks are made up of strings, and the strings are made up of membranes, and it goes on. So at some point, for practical purposes, depending on the context, we always choose And depending on the context, you can treat an atom as a point particle, but you can also at a different level treat the whole earth as a point particle. So for my analysis purpose, it doesn't really matter whether this system and these point particles are atoms or planets in this universe or stars. For our purposes, there is no internal structure, and they are point particles of a certain mass which have a well-defined position vector. बात समझ आ गई? So you can always go down, okay? You can always go a next level and then take, but as you would do, the complexity increases, right? So this, and I can then go on and writing a third equation. Okay, now I can write this for nth particle as well. No? Fn is equal to Fne plus Fn1 plus Fn2, so on. And this you have to be careful. This is Fn n minus 1 because Nn you cannot have the particle exerting force on itself. M3 Rn over dt squared. Now look carefully. You see this force? And this force? They are action-reaction pair. So the vector sum is 0. How about F13 here and F31 action-reaction pair? How about F1n and Fn1? So every internal force has an action-reaction pair. Okay? So if you sum these together and apply, this was Newton's second law, and if applied, Newton's third law, so what you are going to get effectively is this. F1e plus F2e plus F3e Fne is equal to let me just write it simply, m1 d square. Just I'm making the assumption that we have multiplied and divided it with m, and then I'm going to directly write it dt squared m1 r1 plus m2 r2 plus mn rn. Okay, so here on the left you have the total external force, okay, and on the right you have the acceleration of the center of mass, the point at the center of mass with mass m, as if it had the total mass. Okay, now this has been generalized. Okay, this is true for any number of particles. So in a system of particles, every particle would have complicated motion, okay, complex trajectories, except for one special particle, which is one special point, which is center of mass, and the center of mass would behave as if all the mass was concentrated in it, okay, and its position would be determined as mass weighted average position of all particles, and then you can apply this simple relationship to it. Its motion would be determined as if it was only seeing external forces. Okay, so now the point particle assumption that we have been using so far and would continue to do so at least in this chapter, and would try to in the next chapter we'll try to just be a bit more general when it comes to dynamics, when we would have actually rotations. Okay, and rotations are not easy to understand unless we have a good grasp of the concept of center of mass. All right, and that's pretty much it. Thank you very much.